Welcome to week 2. We're still talking about thermodynamics. We are still talking about thermodynamics. We'll actually conclude thermodynamics this week. Here is a picture of a geyser in Yellowstone National Park. You know, Yellowstone is on my list. It's on my list of places to go. This is a geyser. It's called Old Faithful. It's called Old Faithful. And for all the geologists in the room, right, you already know what a geyser is. But for those of us maybe that are new to geology, a geyser it's a hot spring, right? So it's water underneath the earth. It's usually near volcanic activity. And so the earth's core heats up this water, and when it gets hot enough, it actually bursts through the earth, right? And comes up as liquid water and steam as well. So when I was looking at this photo, right, I also thought of another more like everyday practical example similar to a geyser, right? So we create a geyser in our homes when we are boiling water. I got a little video here. Yeah, so we put water in a pot, right? Just like how the earth's core heats up the water in a geyser, the stove provides the heat that heats up the water in a pot, and then eventually the water starts to go from liquid and evaporates into gas or into steam, right? What we call steam. So in a way, right, boiling water is like a practical everyday example of what we see in nature with geysers, right? What we see in nature with geysers. So a question that I want you to think about is, how are geysers and boiling water a display of thermodynamic principles? This is a question that we'll come back to, but as we move through this week's lectures, I want you to think about this question, right? Think about geysers, think about boiling water, and how they display different thermodynamic principles. So these are the 4 topics that we'll talk about this week. We'll talk about spontaneity, entropy. Last week we talked about the first law of thermodynamics, so we'll talk about 2 additional laws, the second and third law, and then we'll conclude with free energy, or Gibbs free energy. So starting with spontaneity, what is spontaneity? What is spontaneity? So think of this question: will a reaction occur naturally at a given temperature or pressure without the exertion of any outside force? Right? This is the question that we're asking when determining if a process is spontaneous or not. So in other words, right, this fancy question that I have here is a reaction spontaneous, right? If it is spontaneous, that means this process does occur naturally under a specific set of conditions without an outside force. If it does not occur naturally under a specific set of conditions and we need to apply some outside force, then it is called non-spontaneous. So looking more into a spontaneous process, right? This is a process that will just happen, right? It will just happen. So what I want to highlight is that there is an initial force. There is something like initially that sparks or ignites the process happening, but we don't need that continual outside force to keep the process going, right? which is different with the non-spontaneous process, right? We need continual force applied throughout the process. So here is an example. If we have hydrogen gas and oxygen gas, if they are together and we give it a spark, right, that initial apply some type of initial force, then it will form water as gas, right? We will basically ignite this reaction of hydrogen and oxygen interacting with each other to form steam, right? Or causing water to become a gas. Let me reframe. We're already in the gaseous state, but essentially these hydrogen gas and oxygen gas will form water in its gaseous state. Now, spontaneity is not related to speed, right? So a reaction is spontaneous does not necessarily mean that it will happen fast. It could. There are cases where it could happen fast, but it could also happen slow and still be considered spontaneous. So here's an example. This graph shows two different isotopes, right, which is shown in red and blue. Two different isotopes and they're decaying, right, which we see over time the amount of isotope remaining. So this is basically a measurement of isotope decay. Now, after 7 days, TC99M, right, this isotope fully decays, whereas U238 does not, right? It's still practically at 100% after 7 days. Both of these reactions, both of these decay processes are spontaneous, but we can see a drastic difference in the speed at which they decay. So if a reaction is spontaneous in one direction, it is non-spontaneous in the opposite direction. And maybe that feels intuitive or not, right? But it's true nonetheless. So this forward reaction, right, going from hydrogen gas reacting with oxygen gas to form water is spontaneous. So if we start with liquid water and right, liquid water going to oxygen gas and hydrogen gas is a non-spontaneous process. So breathe that in, right? If a reaction is spontaneous in one direction, it is non-spontaneous in the opposite direction. So the difference here, right, is if we are so going in the forward direction, remember with this reaction, all we need is a spark. We don't need to keep applying a spark, but if we just apply one spark, this reaction spontaneously occurs. The non-spontaneous reaction will still happen, but we will just need a continual input of energy over time, right? We'll keep needing to input energy for that non-spontaneous process to happen. So let's talk about energy and spontaneity. And I'm actually going to pause here. The next video will come right here to energy, spontaneity.